Hi everyone, I'm going to do another review of linked lists. Yes, I know many of you might be not overly excited about learning about linked lists again. I want to go over that because we're going to be, the reason we're covering linked lists so often is that it ends up covering all the various parts in the course. We look at objects, we look at inheritance, we look at polymorphism, we're going to be looking at abstract data types, how we can implement things like stacks and queues using a linked list. We'll be looking at templating. We'll be looking at iterators. Heck, we could use a model view controller and make a linked list shape, which I've actually done in the past, but I'm not going to do it this term. A linked list shape that you can draw on the screen, things like that. You can use it in a whole slew of different things. It's just sort of a general idea. So here is what we're going to be doing over the next little while. I'm going to be trying to re-record some of the lectures that I did last term, simply because, well, some of them were not up to not exactly what I wanted to say. I might be re-recording this one just based how much I stammered just now. What we're going to be looking at first is we're going to be looking at linked lists again. We're going to look at iterators, and we'll look at templating. Now, the order of the templating versus the abstract data types, that's open for debate right now. But the idea is we're going to be looking at these abstract data types, these ways of storing data. There's more than just arrays. By having pointers around, we can do a lot of really interesting things. And so we'll be looking at trees, we'll be looking at stacks, queues, hash tables even. We will implement, I'm thinking a queue right now, I might change it to a stack, but a queue is easy enough to do, using a linked list. Great. And then we can figure out why what's the point of covering these sort of fundamental building blocks of programming? Because why would I want to reinvent all of these things? Well, because they tell you how to think about a problem, how you break a large problem into smaller little chunks. Much like if you're building a building, one of the big innovations that happened in construction in the past, let's say 200 years, was the idea of mass-produced and regular or standardized building materials. You don't have weird-shaped bricks and blocks, right? When we were living in France for a while, we went to the town of Lyon. There's these beautiful, beautiful buildings and these beautiful walls, all made from these weird-shaped pebbles, just a variety of different shaped pebbles. And what's interesting about that is that you don't see that anymore. Why? Because it's really hard to do. Making a properly shaped wall of a certain standard is next to impossible if all your building materials are different sizes. A brick is a standardized approach. You can build things based on that because you know exactly how it operates. You don't try and get cutesy. Same thing here. We're not getting cutesy. We have particular data structures that have particular characteristics that we can make guarantees about, and once I have that, I don't have to worry about how it's encoded anymore. When I have a linked list, ideally, when I make a linked list for somebody, you just use it. That's the reason we're doing objects. You want something that you can just pick up and use, not have to think about how it was constructed. When I have a tool, I don't think of how it was put together, how it was made, I just use it. We're doing the same thing here. I want fundamental, just basic things that I can get my head around, because coding is hard enough as it is. You don't want to overthink things by making it so that, a linked list, but if I can do this, I can do that. And you don't want these little gotchas, these little edge cases. I want something that is sort of solid and predictable. Then we're going to look at what C++ actually gives us already, the standard template library. There's a slew of different things like vectors, certain algorithms, like searching and sorting algorithms. There's a bunch of collections. There's I'm blanking on the other case, but essentially most of these things have already been created. They already have a linked list in the standard template libraries. You could have used it this entire time. We didn't because we wanted to see how it was built. We want to look at it to motivate how we learn about objects. But there is a linked list already in the standard template library. You could just use it today. Fine. So we'll be looking at that, and then afterwards we'll be doing a review class, hopefully. That will probably be just one of those live classes. Now, There's a lot of different lectures in this next little section. I'm hoping to keep on a particular at a particular pace. Just, you know, if you see that the homework or the assignment is involving a particular lecture, make sure you watch those up to that lecture. But I'm not keeping it to a very tight schedule. Clearly, if I'm babbling this much. Okay, so we're going to be reviewing object-oriented design. We'll be looking at our linked list class, our doubly linked list class again, and then we'll look at iterators and templates. And then afterwards, not today, but later on soon, we'll look at stacks and queues. And I will live code a stack. I'd like to point out that I have a slew of different linked list slides in here that I'm not going over. I actually hid them away for here so that we don't actually have to even discuss them or address them. The reason is I want to have those available to you so you can look at one implementation of a linked list, and then look at my code and look at a different implementation of a linked list. Choose whichever one you like more. Well, don't tell me which one you like more if you like the other one more. If you like mine more, go ahead and tell me. The idea is there's a million and one ways to develop these things. We all have different approaches, and seeing different tactics can be useful. The linked list code, for example, in the slides is streamlined, it's stripped down, but at the same time it doesn't have a lot of the sort of more robust coding principles involved, right? They're using a friend class, which I don't tend to suggest doing, for example. So I'll be mostly skipping the slide code, but I left it around just in case you want to see it, just in case you want a different approach to look at linked lists. So here's linked lists with Eleanor Roosevelt in there. By the way, in case you don't know who Eleanor Roosevelt is, that's this lady here. All you need to know is who's in front of you. A conga line just requires the person in front of you. You don't need to worry about the person behind you or how many people are behind you. You might, if the person's creepy, you might want to worry about the person behind you, but other than that, you know, you don't have to know. You just need to know who's in front of you. And it can get infinitely long. If you go to a wedding, you'll see this in action. These conga lines that'll go down like 100% long. You don't have to worry about running out of size like you do with an array. You just need each node to know who it's connected to. That's the principle. That's the idea. That's why trees also, it's a very similar approach. Trees have infinite size. So our motivation is, if I had an array, let's say, and I want to insert something in the array, what happens? I remove something. I would need to shift all the elements over and then put in the new element. It's an extremely expensive operation. If someone's going if I want to insert something at the very front of an array, I gotta shift everything down, especially if it's in some kind of order. A linked list doesn't have that issue. A linked list allows me to just insert it wherever. I have to find the place to insert it. That may take some time. But once I know where to insert it, it's constant time. And it's effectively unlimited size. So with an array, we've seen this. When I run out of space, I got to transfer everything over to another array and then add the element. That takes a lot of steps. If you have 20,000 elements in your array, that's going to take a little bit of time. If you have to do that all the time, it's expensive. A linked list, you just insert it wherever you need to. So I like to think of it like people waiting. A barbershop also works, but you don't have people missing an arm. If you're waiting at a hospital or waiting in a hospital, let's say, you're waiting in order in which you arrive, but it's a priority queue essentially. It's first come, first serve. So that's what a queue is, what you normally do for a lineup. But it's a priority queue, as in somebody comes in with a missing arm. What happens? They go to the front of the line. They're about to die, right? And what should you do? Everyone would shift back in the line. If someone goes, it's not worth it, gets up and leaves, what happens? Everyone in the back has to shift up one seat. A linked list allows you to just remove the seat, essentially, and rehook it up. That's why we do it. Okay. Moving everyone every time is a very expensive operation, and the linked list avoids that. So here's our approach. We have each single data node, let's call it a data node, has some data, something it's wrapped up, that it's storing, like the cargo container of a train, and each car of a train connects to the one in front of it. So all I need to know is where to start. So my linked list points to the very first node, and that points to another one, that points to another one, that points to another one, that points to null at the end, and I'm done. If I want to add an element, let's say I want to add it here, what do I need to do? Well, first of all, I need to hook up this new element to this element here. I need to point this next to this node here. That's step one. I cannot lose what I'm pointing to. Okay, so I'm going to make some space visually. I hook up this node to this. Now I have two things pointing to the same node, and you'd think, hey, that's wrong. It's not the end of the world. Next step, because now that I've had them both hooked up, now what do I need to do? I need to hook up this to this. If I hook this up first, I'll lose this part here. So first I need to hook up this node to this, and then afterwards I hook up this node to this. There is an order I have to do things, otherwise I lose the connections. But I change 2 pointers and I'm done. Adding pointers, adding elements, cheap. It only takes 2 pointer changes. Finding where to insert it, that requires walking down the linked list. That can take some time. Finding something at a particular index takes time. I have to walk down the linked list. I can't just jump to my array. So our linked list, you could have it so they have a first and a last. I like pointing out the fact ours doesn't have a last. You don't really need it. You can have it, but it's a bit more bookkeeping. If I want to get the last, I just walk down the linked list and get it. It's not critical. A doubly linked list, however, you should have a first and a last. And this is what we looked at when we extended linked list. Instead of just a first and all of this material, I added a layer here and an object here. Everything else is exactly the same as I had before. There is nothing new, right? Those are the new parts. So why don't I just use the code and the variables that I had in a linked list in the child class? That's the idea of inheritance and polymorphism. That if I inherit from the parent class, I don't have to do this extra work. I don't have to make another first variable. I already got one. I get it for free. And if I have getNext as a function, I get that for free. Fine. If I want to, print out something in particular that's specific to a doubly linked list, polymorphism allows me to call the function for the linked list, and it chooses the right one, the right function for the right circumstances. So we'll briefly go over code again, but let me point out a couple things. So I have nodes in my linked list. I have the list itself. That list itself just wraps up, much like calling a train the train. A train is actually a series of cars, but the entire thing you call a train. A linked list is a series of nodes hooked together, but the whole thing together is called a linked list. So I definitely need the nodes because they need to hook up to the next thing. My linked list itself, it's semi-optional. It's a better way of doing it. You want to wrap up all the gory details of all these nodes connected to each other. You want to wrap them all up in one class that other things can access. So I want this sort of interface, this way of abstracting away how it's done, and just say it's a linked list or it's a list. The iterator is the optional thing, but I still think it's a very useful thing. It's getting more and more popular. So here is what we have. As a general rule, with a linked list, what do I care about? What do I not care about? Number one, I do not care how the data is stored. I care that I have data. I really don't give a crap how it's stored. Number two, I don't care how the linked list is hooked up. Is it an array? I don't care. Is it, some series of pointers? I don't care. I want something like the super storage-o-matic. I want something that can just store values for me and give me those values back. That's all I really care about. I don't care how it's implemented, or I shouldn't care how it's implemented. If I have to know how it's implemented, I've designed my code wrong. Because if I have to know how it's implemented, now no one can just pick up and use a linked list blindly. It's not if I have to figure out how to, let me think of a good example. Why do most of you use an iPhone? Or a large number of you use an iPhone? Because you have a device that you know works. Most of you are not going to hack your iPhone. It's an appliance at some point in time. You're not worried about the computer that's in your pocket. You use it as an appliance. You don't think about how it works necessarily. You're not digging into it. You don't try and hack it. With a computer, a lot of people hack it. They're looking at the BIOS and they're doing all sorts of crazy things. At some point in time, if it's abstract enough, if you make it simple enough, if you make it so that you don't have to know how the internal guts work, people stop worrying about the internal guts and just use it as a tool. I don't look at my drill down in the basement and try and figure out how it works. I just use it as a drill. That's what I want. I want a tool. So I don't want to know how it's hooked up. I just want to know that it works. So I need to be able to get the next value. We're going to say that that's a requirement here. We need to be able to get the next value and the next value and the next value, so I know I can get all my values. I need to get the value at a particular element. So I need to be able to get all the elements and each element, the values for each element. And I just want the data to be stored. Okay. This is why iterators are needed for vectors when we look at standard template libraries. Because if I don't have that, I need to know how a vector was implemented. I shouldn't have to know. That's the point. So this is what an iterator is all about. An iterator is just yet another class, and it's essentially this. It's your finger, or this as well, this mouse pointer. It's you pointing at what you're looking at now. How does it work? You don't want to know how it works. You just know that whatever it's pointing to, you can get the data for. Particular kind of data. You don't care how it's being stored or anything like that, and I can go to the next element, the next element. As long as I don't have to know how it's implemented, it gives me some flexibility in how I code things. So it's essentially just like a pointer. It points to things, points to a position in my linked list. It returns the data. I should never know that there is even a linked list node. That even the concept of the class should be completely foreign to me. Anyone using a linked list, when I'm done with this, everyone using a linked list knows that there's something called a linked list. They know there's something called an iterator. Yeah, oh, and then it stores data. That's it. And if my iterator is general enough, I don't know how that's been implemented. That's the point. It should be a tool. So we can return the data. We want to be able to get the previous or the next. I'm only going to do the next in this case. And I would like to be able to know that two iterators are the same. They're pointing to the same thing, right? If two fingers are pointing to the same word on the page, well, then it's the same. Then they're equivalent pointers. That's what we want. It's an iterator. It allows me some general sort of abstract way of walking through or iterating over a list or iterating over a set. So I could have an iterator that points to elements in an array. I can have an iterator that also points to elements in a linked list. And I shouldn't know what it's pointing to. It just gets me the data. That's the concept. So an iterator could be applied to arrays, linked lists, stacks, trees, whatever. And I can get the next, get the next, get the next, and get the data. Here's what my iterator class is going to effectively look like. I will have, an iterator. Maybe I want to take in some value that it's going to be stored. No, it doesn't store anything. I need to be able to get some value. Whatever type of data is being stored in my linked list, which is a key. When we get to templates, it's just going to be T. It's going to be some kind of data. What kind of data? I don't care. Some kind of data. I'm going to be able to get the next, and I'm going to be able to see if two iterators are equivalent to each other. That's it. Notice there is nothing here that says node. In public, the things that everyone is able to see, nothing says node, linked list node, or anything like that. I need to be able to my linked list. So I'm going to be going over that code itself. Essentially, I'm just going to move on to get the next. My linked list code itself is going to have some way of inserting and erasing, or I think it's insert and delete, or insert and remove in my code. So I insert an element at a particular point. So I insert a string in this case wherever this thing is pointing, or immediately after wherever this thing is pointing to. I insert a string. In our case, it's going to be inserting a number. And I could say erase whatever this iterator is pointing to. So, and it returns the iterator, the pointer to the next item in my linked list. I should be able to say what the beginning position is. So linked list should also support this. Just what's the very first element in my linked list? What's the first element of my array? This should be applicable to any kind of data storage you have. An iterator should always just work. And I can say what the last element is. So here is how I get the beginning. I make an iterator, I get the position, and say that the position it's pointing to is the very first element of my linked list, and I return it. That's it. How do I get the last one? You can either get null, or you can get the last element in your linked list. I'm going to do the last element of my linked list and return it. And if I'm going to insert a node into my linked list, I know where my iterator is. I just need to get the so I'm going to insert at the back. If the iterator position is equal to null, so I'm already at the back, I just insert at the back. Otherwise, I know where the iterator is. I'm going to make a new node. I'm going to stick it immediately after this iterator and hook it up, like what we did with that animation, right? I know where I want to insert this thing. I'm going to insert it behind whatever this thing here is pointing to. And if the before, so you don't need to have a before, but you could have a before. If you know the previous one and it's if it's null, then I don't have to worry about that. So what I could do is just see, I'm just always going to be inserting after that iterator. So unless that iterator is pointing to null, I'm just going to always insert at the end, insert after that point. Okay, erasing a particular element, I know where my iterator is. I will need to get the element just before it, technically, and I will need to be able to get the element after it, and I just hook those two up. So I get the element before, I get the element after what I'm currently pointing to, and then I hook the element before to the element after, and I'm done. We've already done that function, and so we can do all these sorts of things. I can insert at the back, I can insert a particular place, or insert a particular element after position pause. So position pause is equal to the beginning. I move 3 positions over. So I'm now pointing at the 4th element. That would be sort of the back. So it would be Rami would be the person I'm pointing to right now with this pause. I'm always inserting at the back, so Rami is the only person in the linked list. Then Najle and Zachariah, and then Jennifer. So since it's going in the reverse order, Jennifer would be the end of the list. Yeah, and this would be inserting at the back. So actually, it would be Rami. Jennifer is the 4th element of the list. Rami, Najali, Zachariah, Jennifer. Okay. So I'm pointing at Jennifer. I'm going to add Antonia, and that is going to be immediately after Jennifer, and then I can print the whole thing out. And then afterwards, I can go to the beginning again, get the next element, so Najle, and then erase Najle, and then print it all off. And so I should get Rami, Zachariah, Jennifer, and then Antonia. Okay, let me do some live coding here, and I'll look at how we're doing for time. Okay, let me do a brief pause, and I'll actually pause the video this time though, and then we're going to do some live coding just to see all of this in action. Okay, we're back to recording. I'm going to do the live coding demo. I'm just going to use the lecture 12. It's not lecture 12, but the polymorph lecture when we were looking at linked list, and we were looking at linked list. We have a doubly linked list. We have linked list node, doubly linked list node, linked list, and a linked list node. I made this linked list iterator. It has next to nothing in it. Linked list itself, linked list iterator itself, the CPP file, has nothing in it. So just letting you know in advance. Let's review what we looked at before though. Here is a linked list, right? It has a constructor, even has an operator overloading, so I can add two linked lists together. You pass me some linked list. Oh, sorry, it should be, if you just plus and then put some kind of linked list data in this thing, it gets added at the end of your linked list. I can insert at the front, insert at the back. I can go to, I'm going to be implementing these things here. I said 13 in the other one. I can remove from the front, remove from the back. I can see if this thing is empty. And if when we go into linked list, doubly linked list.h, the things we needed to override, inserting at the front was different, so I overrode that function. Inserting at the back was slightly different. These are virtual functions here, right? So I can insert at the back. Inserting at the front actually probably should have a virtual in front of it. Removing from the front, removing from the back. I'm thinking they're going to be, let's have a look. Remove from front, remove from back. Okay. So if I have a doubly linked list, I don't actually need to override those functions whatsoever. Printing, however, does need to be overridden. Okay. My linked list nodes and my doubly linked list nodes, same sort of thing. What I need to do for this is every time I make a child class, I need to figure out what's different from the child class to this, from the parent class to this new child class. Is printing different? If so, I need to override that function. Is inserting something at the back different? If so, I need to override that function. That is what you need to do with all these classes and these child classes. You need to figure out who needs what kind of, do I need another, so in this case, I have a brand new function that I didn't have before for a double linked list, is getting the end. So that's a brand new function. And I have a private variable called pend that I might need to have a get end or something like that. Well, here's it, get end. Wow, almost like I thought about that, right? So if I need the end, I call get end. I don't have set end because inserting at the back is already done. I just need to think long and hard every time I make a child class what I can take from the parent. I'm trying to do the minimal amount of work possible. When dealing with my parent, I want to use as much of the parent as possible and just tweak functions and variables the minimal amount. I want the minimal number of new variables. I want the minimum number of new functions or overridden functions. So insert it back. These had to be overridden. I had to define them again differently. Same thing with print. That's all we do when it comes to inheritance. Okay. Let's get back to my iterator. So I had this linked list, which by the way, I don't think let's look at this again. I need an iterator to get the beginning. Okay. I need an iterator. I need something to be able to get the end, the last element. Okay. I need to be able to remove an element based off the insider. I might need to override that one. We'll see. And I might need to override the inserting, so removing from the inside and inserting from the inside. I might need to override those in linked list in doubly linked list.h. So let's make those virtual. Didn't even think about that until right now. Okay, great. I'm going to need to implement all of these functions, and that's what I'm going to do with my iterator. Actually, before I get there, because I don't want to get too far ahead of myself, I'm going to implement what the linked list iterator is going to look like. It's actually just an iterator. And I think what I'm going to do is actually use this for templating later on. So here we go. There we go, laziness. Do I need a destructor with my iterator is one of my questions. That's why I have it as a commented out thing. So we will look at that in a second. When do I need a constructor? When do I need a destructor? I would say I need a destructor anytime I call new, for example. If there's a call to new, or if I'm getting new memory or allocating memory in my constructor, I need a destructor. If I need to break something down afterwards, when I'm finally giving, the objects being destroyed, if I have to break something down, like I have to set things up so that they're safe values, destructor, great. So if I have to set all my values to null, destructor, great. But if I don't need to do anything like that, I don't need a destructor. If I don't call new, I don't need a destructor. So let's have a look at what linked list iterator has. Does it have anything inside of it? It does not currently have any parameters. These are going to be public methods. Great. It will need something. So let's make it private. And what am I pointing to? Well, I'm pointing to a linked list node. The current linked list node that I'm pointing to. I could, if I wanted to, if I need to get the previous, I could also keep track of the very, very first linked list node that I have. The reason for that is I might need to, go back to the very beginning and then walk back to find that element just before. Okay. Do I need a linked list itself? No, I don't need the linked list itself. I just need the node that I'm currently pointing to. And when I say get, I'm not going to even get the node I'm pointing to. I'm just going to get the value for the node that I'm pointing to and return that. Okay, let's save all this. So now I might not want that. So let's see what I could do here. I would like the constructor to always have, so I need an iterator, I need to be able to make a constructor, I need to be able to set it up. Well, that should be fine. So I'm going to make the node equal to null. I'm going to get rid of this. There's no need for a destructor. I'm going to get my particular value. Okay, so if I'm going to need some kind of safe value here. If p node is equal to null, return -1, let's say, but that's not a very good thing to be returning, or let's return 0. It's not a very good indicator that something went off the rails, but I do want to check to make sure that nothing's going off the rails. I'm going to return p node. So does a p node actually have the ability to get the value? That's the question. Print node get next is end get next. I want to get the data. Oh, it's protected. I'm going to need to change that. Or I'm going to have this as a public method. Oh, or sorry, I need to have it as a friend class. So let's say I can always get the data from a node. That shouldn't change anything. It might need to change double linked list node. Get previous, get data. Nope, didn't have to re-implement get data. Sorry about that. So I'm going to go to my linked list iterator and get data. Oh, that's what it was. It's not an int per se. This is a, what do we call it? I'm trying to figure out what that. Let's go to my doubly linked list node. and have a look at what this actually is. No, that's not linked list node. This one, linked list data, is what I actually needed. We'll see how we can make it into a template very, very soon. So, linked list iterator, linked list iterator. I'm going to go here. All right, get. All right, what would be a blank value for? Oh, it's just a particular value. Okay, so I'm going to call get data, just return the data. Otherwise, I'm going to I'm just going to set that up and I'm going to return data. All right, I'm just returning the value that I had. How do I get the next? Well, if p node not equal null, p node is equal to p node do that. I may not be able to, let me see here. I should be able to go all the way to a null at the end, but maybe I don't want to do that. Maybe I just want to stop when I'm at the last element. So get next not equal to null. All right. So if I can move back one space, I will. Otherwise, I will leave it alone. So in this particular implementation, I will walk down my linked list until I get to the very last actual node. Not a null, but the actual node. Okay. And I want to see if these two things are equal to each other. So what could I do here? Well, turn this is equal to p iterator. I could do something like that. If we just want to compare pointers, or I could do this. So if p iterator not equal null and p iterator p node is equal to, that should do, that might work better. The thing p iterator is pointing to is exactly the same thing that p node is pointing to. Or I can get the value for each of those nodes and just say that the same. But you could have the same value throughout your linked list. It doesn't mean it's the same thing I'm pointing to. What we're saying is these two iterators are pointing to the exact same node. So that's, I don't even need that part. So if p iterator is not equal to null, and I don't even need an if statement, return and this. If this is true, I want to return true. They are exactly, they're pointing to the same node. If this is not true, then I want to return false. So I don't need an if statement, I just need to return that Boolean itself. And I'm done. Now we're going to have some weird quirky things presumably with the linked list node. This is an override specifier. I have not implemented any of these things. That's what this is yelling at me for. So let's do linked list. We're in linked list.h. I want to go to linked list.cpp. Let's just plop it down at the bottom. One more, up a bit. And let's also just steal this because I'm lazy. Boom. 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 Okay. How do I get the beginning node of my linked list? Well, I already have that. So return. So I need an iterator that will do this. So I need an iterator, LL iterator. Is that how I spell it? Excuse me, iterator, I hope so. Iter. Okay, and then depends then if I want to make a new one or if I just want to use this. Iter dot. What I want to be able to do is set the iterator. I may not be able to set the iterator. I may need to set my iterator. I could also just make it so that I can't have an iterator without one of these things. But then I would need to know what the node is. Okay, so let me see the best way of doing this. For the time being, I'm going to, what's the best way of doing this? Because what I want to do is actually have the node and not know that I'm storing a pointer to a node. I just want it to be able to work with it, whatever you give it. So it's pointing to something, and then I can call next and move to the next one. The actual code knows that it's pointing to a node, but nobody else should need to know that. I'm going to have to do it this way at least. P. No. P. Let's call it node. Okay. So I'm going to change it around a little bit to say it'll take in a linked list node automatically. And I'm going to change iterator so that when I get this, and that should have been a single equals instead of a double equals. Okay. P node is equal to node. Great. Linked list.cpp. Okay. So I'm going to make an iterator and I'm going to pass in the current node. So this get start. That'll make an iterator at the using the starting position, and then just return that. Great. If I want to get the end, I would do the same thing. All right. If I want to, this is just going to make an iterator pointing to either the start or the end. Okay. Removing something from the inside. Well, I need to figure out where I'm pointing. That iterator is where I'm pointing. I'm going to remove that element, see if there's an element behind it. If there is, hook it up with the element before it. Okay. So I need to figure out what node I am dealing with. Okay, so what's the best way of doing this? But notice I shouldn't have to say where it's located. So what I could do is, do I have a find function here? I need to find the element before the one I'm looking at. Okay. Let me see here. I actually do want to know what this linked list node. Ugh, that's an ugly solution, but I'm going to do it anyways. Okay, so current pause is equal to start. So I get the starting point, and I want to see if it's going to begin, not start. There we go. So I'm going to get the starting position. That's going to give me that particular iterator. What I need to be able to do is see if that iterator is equal to this other iterator that we have. Will that work? So I can begin there. This is one of those cases where if I do the code slightly wrong, it's going to make a big problem for me. What I want to be able to do is I want to start off the iterator at one particular position. I want to be able to walk down this thing. I want to be able to that's the way we're going to do it. Okay. Current pause. I can make this iterator. I can make iterators each and every time through a loop. And once that iterator is equal to the thing I'm looking for, this parameter coming in, then I'm fine. Then I can stop. Or I stop when I get to the end of my loop. I might want, the easier thing would be to make the iterator know about and be able to return what node it's pointing to, but that sort of breaks the illusion of not knowing what's hooked up to what. So let me change here. I'm going to walk down my array. So we already had one of these already. Okay. This is me walking down my array. And what I'm going to do is as I walk down my array, I'm just going to keep on making a new iterator. And I'm not going to call print node. I'm just going to make a new iterator each and every time. I'm going to get destroyed every single time as well. And it's going to be p cur node, what I'm currently pointing to. And then I want to see if iterator dot equals cur pause. So, and it has to be a pointer to cur pause. Okay. If the iterator is equal to cur pause, then I'm going to return. So I don't want to return it yet. I want the element before it as well. Previous node is equal to null. Okay, so I have my current position is going to be incremented. And it will just keep on calling get next. Okay, if the current node is not equal to null, I'm just going to keep on going. When I know the iterator is equal to this, well, if I know this, that the iterator is equal to my current position, then, and I have this previous node as well, what I need to do is hook up the previous node to the node afterwards. Okay, that'll work. Okay, so I found what I'm looking for. I know what the previous is. Then I need to say, and I have the current node, so p so if previous is not equal to null, p previous node set next is going to be equal to current node get next, whatever that ends up being, and then I will at least in this case I'll be hooking that up, and then I found the element that I'm looking for. I take the previous, hook it up to the next, the last element, the element afterwards, and then beyond that, do I need to do anything else? If I was a doubly linked list, which would be the other instance, I need to hook up the pointer the other way as well. But I don't have that particular issue, and it should actually just be removed as a result of that one little step. Great. and return true, and we're good. If I don't find anything that I'm looking for, return false. Notice this is not the same as, you're probably wondering, why do all this extra work why have this iterator crap at all? Why not just pass in the node that you're looking for? But then this function is exposed to the outside world. If I do not know, if I have to say, oh, by the way, pass me in a linked list node, then whoever's using a linked list needs to know what a linked list node is. An iterator just says, I have some kind of iterator. It's this generic approach to doing things. If I have the right designed iterator, it means I don't have to know anyone using this thing. I'm pointing to the next in my array. I don't care how it's implemented. The iterator allows me to hide this. I still have to do a lot of work inside the linked list class. I just don't have to do it. I just don't have to expose that to other people. This is information hiding, one of the other topics we've been talking about. Okay. So I have one more, which is insert inside. That's going to be doing almost the exact same thing. I'm going to get the previous, and I'm going to get the current. So I'm going to get lazy here. Okay, the thing I'm going to be looking for, I'm going to make a new linked list node. New node, and it's going to have it's not a data value. I'm going to have to change that one. There's my iterator. Because if you remember, we don't have just a number, we have a data, some kind of data value that we're storing here. There we go. And linked list .h. Okay, there we go. Yep. Okay, I'm going to insert this value inside the linked list after this position right here. So what I need to be able to do, what I probably should have, is some way of identifying or finding a particular iterator based off of a given iterator. Would that work? Yeah, it would probably be the more general solution if I wanted to do that. So what this is actually going to do, I'm going to get the previous node, I'm going to get the start node. I'm going to keep on walking down this thing. I'm going to make a new node, which is going to have a data val in it. That should hopefully work for me. So I have a brand new node. I actually might want to call new on this one. New node, because these are actually permanently stored. The data value. Okay, I'm going to walk down my array. I'm going to find the iterator where the current position is equal to the iterator that I'm finding. When I find that, when they're equal to each other, I have a previous and a next. I got to make sure that the previous is not equal to null. So I can set the previous to be so I had the previous. I actually don't need the previous in this case. So let's remove that for a second. I just need to keep on getting the current node until I find it. Once I get the current node, what I'm going to do is I'm going to say p new node. I should have done it. I must have some kind of error in here. Hold on. Because, oh, there we go. It's data val. Linked list node is, what does it take in? I make a linked list node with a particular data type. That's what my constructor says. All right. Okay, that shouldn't be a problem at all. Why is that yelling at me for? Oh, I have a problem here. Insert inside. It's right up there. So if I go back to linked list here, insert inside, that's the issue that I have. Why is that not? LL iterator, LL data, data val. There you go. That's the issue. All of that for a semicolon. Told you, they're everywhere. They're the great problem for all programmers in C. Okay, so I have a linked list, a new node. I'm going to, what do I need to do here? I'm going to set my next for the new node to be equal to the current current node and get next. All right, so I'm going to get the next for the current node, make the new node point to that other thing. If then I'm going to have p current node set next, and it's going to set to p new node. All right, I don't need the previous thing here. I can get the next each time. If I can't find the iterator, I just return false and nothing happens. So I could actually, what I might want to do here, delete p new node. If something horribly went horribly wrong here, I need to delete that. I just called new and it's not actually hooked up anywhere, so I need to delete it. Okay. I'm not sure if that's going to do everything for us, but it might enough. Okay, begin override specifier. And begin and end, those are okay. LL iterator. I'm going to look at this in a bit more detail in a second. This would actually be using an iterator, allowing me to add elements without having to know how a linked list is stored. I could just get the front of my linked list, and let's give an example of this in action at least. I can make a linked list. I can say ll dot start. Is it begin? Begin. That's the start of my linked list. I don't have to know what a node is. I could just get that. I can then call ll dot next. I could have a while loop that says while ll. So let's. This is gonna begin's gonna give me something. Hopefully that's going to work. Okay. While iterator does and let's do one more. If I can figure out what the end, the start and the end are, and then I say, well, it's not, as long as it's not equal to enter end. So as long as we're not at the end of my list, I'm just going to get the next element. And this is iter.next. I'm going to get the next element each time, and maybe I want to get the particular value. Okay. maybe I have a cout statement that says node has value, and then some kind of output message data dot num. All right, I want to look at see how my there we go. So notice again, I'm getting the beginning of my iterator, the beginning of my linked list. I can keep on walking down my linked list. I'm going to get the next each and every time. Each and every time I will increment where I'm pointing to until I get to the end of my linked list, and then I stop when I get to the final position. At least in this case. That's all I need to do. And I can access and get the values for elements in my linked list without actually having to know how it's formed. Otherwise, what do I have? Without this, without an iterator, what do I have? I have ll.get, can I get an individual element? I don't think I can. Is empty, remove from back. I have nothing to get the individual elements. I might have something to say get element I or something like that. I could have implemented that. But I don't really want that. I just want to say, like, give me the next element, give me the next element, without knowing how a linked list is actually made. That's the point of these iterators. I'm going to clean up the iterator class a little bit more off camera, adding it to the DLL, the doubly linked list.cpp class. But here's the kicker about all this. When we look at this again, I'm going to clean this up so that my iterator, I don't even know that it's actually using some kind of special data. I'm not using something like an LL data. I'm going to use any old data. That is another thing altogether. Is this going to be some way allowing, so when we look at templates, will allow you to store any kind of data that you want, provided it fits a certain set of criteria. Okay, hopefully that fan on my computer is not too loud, but I'm trying not to wake up my kids. I'm recording this at night. I'll also fix up the code to make sure it all compiles and all that kind of stuff. But this is just the first step at looking at an iterator. It is, I want to hide away the fact how this thing is implemented, and I have a standardized approach allowing me to go element by element through whatever data structure that I have. Okay, we will see iterators again when we look at the standard template library, or standard template library. All right, thank you everyone, and have a great night or day whenever you're watching this video. Thanks.